All right, so we are going to do some more stuff with this face detection. As we left it last time, we had this little test code where we had our original person image, and then we ran our edge feature, and this is 10 pixels wide, 6 pixels, no, 10 6. 10 6 is the upper left corner. It's 12 pixels wide and 8 pixels tall. Okay, and it returns the feature value for that image, and that's here is this value -420. Okay, now one other thing we could do is we could do a loop. Let's see. Maybe we could put all of this in a loop. Where
how did you do that?
I selected all of the lines with shift and then the arrow key, and then I hit tab, and then it tabbed it all in. It's a nice little trick.
Can you untab it that way too?
Yeah.
Because I have.
Yeah. So you can select it all and then do shift tab.
Yep.
Goes back. Okay. So let's go ahead for I in range. Let's do 10 of these. So we're going to do 10 images, and we're going to load in each of these I images, do all of that again for each one of them, and not forget our colon there. And so this is going to calculate the feature values for the first 10 first 10 faces. You know what? Let's move that. Let's put this back to 6 6 and 6 4. Let's try this. I want to try and get that thing where it's over top of the guy's actual face. Let's see. There we go. That's sort of on the nose. Let's move it up. Also, if we put in here a plot.pause, we should be able to see all of the different images as they change. Let's make this have the vertical position be at 3, and we'll make it taller. Let's make it be 8 tall. Let's see, what's that look like? No, I want to move it over to the right. I changed the wrong one. That's 6. What's this one? Let's see. What is that? Where does that go? There we go. Okay, so that's kind of over top the nose. Maybe if we move this up to 4, maybe. Let's see. No, that didn't. That moved the other way. That needs to be the 4, maybe. There. Okay, so that's kind of over top of the nose. Okay, and here are the values for the first 10, the feature values for the first 10 pictures that are faces. Okay, and then I'm gonna and then let's run. I think it's called non-face. Is that right? Yeah. So here are the first 10 that are not faces, and so, oh gosh. So some are small, some are relatively big, but in general, these ones are more negative. You notice how there's more large negative numbers for the ones that were faces than the ones that were not faces. Okay, so there does seem to be some information here with that feature to help us discriminate between faces and non-faces. So you could imagine, well, let's say, if the feature value is greater than 0, if that feature value is greater than 0, I'm going to classify it as a not face. And if it's less than 0, I'll classify it as a face. And so 1, 2, 3, 4, 5, 6 out of the 10 faces would be correctly identified. And 1, 2, 3, 4 of the non-faces would be correctly identified. Okay, so that would be better than 50% overall. So that would be a valid weak classifier. Okay, so what I just did there is I was looking at that information and I decided on some threshold value for this feature to determine whether it's a face or whether it's not a face. So I picked a threshold. I said 0 in this case, and I said if the feature value is less than 0, let's classify it as a face. If the feature value is greater than 0, let's classify it as a non-face. So I took the feature value and I used two other pieces of information. One of them was a threshold value, and the other is which side of the threshold is a face and which side of the threshold is not a face. Okay? So in order to turn this feature value into a weak classifier, I needed two other things. Okay? Which side of the inequality is the face, and which side is the non-face, and what is the threshold that determines where that determination is. Okay? And that's what we have in this equation right here. Okay, so like I've said before, understanding the notation and seeing, just what I described in words makes sense. And of course we could write that in words, but it's cleaner and easier if we can get it into a mathematical equation, especially if we're going to try and translate that into a program. It's easier to have an equation to deal with than a word description. Okay? So, of course, I've only looked at one feature right now, but we know there's like 180,000 different features we could have. Okay, so we need to distinguish between all the different features. And in this equation, we distinguish between the features with the subscript j. Okay, so when j is equal to 1, I'm looking at feature 1. When j is equal to 2, I'm looking at feature 2. Feature 3, feature 4, all the way up to 180,000. So j represents the feature number. And I could have a weak classifier. I could build a weak classifier based on each individual feature. So for every feature, I could have a weak classifier. Okay? So J represents which feature I'm going to deal with. And the F, okay, the F there is the feature value. And that sort of corresponds, you'll notice in the code here, when I returned the value from the edge feature, I stored it in a variable called f. And I purposely did that because that f matches with the f that's in here. Okay? That f is the feature value returned by the jth feature. Now, every feature can be evaluated with a different image. So every image has its own feature value. Like over here, this is the feature value for one of the non-faces. That's the feature value for a different non-face. So every image you can send to the feature, and it will give you a feature value based on that image. So in this notation, x represents the image that you're passing to it. And so in this sense, in this mathematical sense, x is all of the possible images in the world. And we're going to pick one particular image, stuff it into this f function, which is the feature, and that function is going to spit out a value that is the jth feature's value, f, given that input image, x. So x is our input image, f is the feature generated from that image for the jth feature. All right? So that's what fj of x is. It's the jth feature value for image x. So then we need to turn that feature value into a weak classifier's classification. So hj is the weak classifier's classification using the jth feature given an x input image. So h is either going to be 1, that it thinks that feature, that weak classifier thinks it's a face, or 0, where that weak classifier thinks that particular image is a non-face. Okay? So if an h value is 1, that means it thinks it's a face, and if the h value is 0, it thinks it's a non-face. Now, of course, it could be wrong, and as long as it's right and more than 50% of the time, then this feature is useful. Okay? So hj of x is the predicted classification using the jth weak classifier. Now, how do we determine whether that weak classifier gets it as being a face or not a face? We're going to take the feature value and we're going to compare it with a threshold. And theta here is the threshold value, where in the example that I just gave, that would be 0. So theta j would be 0. And there's a subscript j on there to represent that each feature, each weak classifier, has its own threshold. So I don't have to use the same threshold for every feature. Every feature can have its own threshold. So theta j is the threshold for the jth feature to determine whether that weak classifier thinks it's an image, a face or not a face. Okay? So that makes sense. I'm going to check, is the feature value less than this value theta? Okay? Now, in the case that we had just as the example, if the feature value was less than 0, we decided that should be classified as a face. So that makes sense in this equation if we ignore the p. Okay? So if f is the feature value is less than the threshold 0, then it will be 1 a face, and otherwise it will be a non-face if it's greater than or equal to 0. Okay? The p is in there to allow us that it might be that the feature values were large if it was a face and they were small if it was a non-face. Some features might be that way. Well, one feature in particular is if I took this and, well, never mind. So some features might have large values when they're a face and small values when they're not a face. So I would need to have that equation be, if f is greater than the threshold, then make h equal to 1. Okay? And the way we've done that is with this value p. And p, they call it a parity. Okay? And p is either a value of 1 or a value of -1. So in the example that I just gave, we would have p as being 1. So I multiply the left side by 1, multiply the right side by 1, and it's still if f is less than theta. Okay, so when p is equal to 1, the equation is basically the same. Okay, and again, there's a subscript j on there that each weak classifier can have its own parity, just like it can have its own threshold. Now, in the case that p is -1, I'm multiplying an inequality by -1, which I don't know, maybe you have to reach back to high school or something when you learned about inequalities. But if you multiply an inequality by a negative number, it flips the direction of the inequality. It makes a less than sign a greater than sign. And if I multiply by -1, it flips the sign but doesn't change anything. Okay, so if I choose the parity to be -1, then that says, is the feature value greater than the threshold in order for it to be determined to be a face? So it's a very clever way of using the mathematics to allow for both possibilities of a feature being greater than and a feature being less than. Okay, so you don't have to have an if statement. If I want this to be greater than, then use this equation, otherwise use this other equation. Instead of the if statement, you build that binary thing in the if statement into the value of p. It's very clever. Okay? So this is a nice compact way of writing a mathematical equation to represent this idea, is it greater or less than some particular threshold for the jth feature value given any particular input image x. Okay, so it's complicated, but it makes sense. It's a nice compact way of showing this. Have you guys seen this notation before, where you have a curly brace and then multiple rows and then the colon to say, in this case it gets that value, in this case you've seen that before, right? So basically, if this thing here is true, then it gets 1. Otherwise, it gets the value 0. Okay, so that's basically a fancy way of saying, if the top thing is true, then set hj of x to 1, otherwise set hj of x to 0. Okay? It's a standard mathematical thing, but it's not very common, so you're excused for not remembering that that's how it works.
I've seen it before, I've just not seen it used like that.
Yeah. Got it. Okay? So now we're able to produce these weak classifiers. So now you know, Justin, how to use these feature values that you've created.
Yes.
Okay? So what I have done in the classifiers.py file, I have created a class called a weak classifier class. Okay? And the way I've organized this is that in the constructor, you're going to pass to it what kind of feature is it. Is it an edge feature? Is it a line feature? Or is it a checkerboard feature? What I call that diagonal, I call it a checkerboard. And I made them be just a string. So I have a string of edge if it's an edge, a string of line if it's line, a string of checkerboard if it's checkerboard. Okay? So you tell it, you've got this weak classifier. I'm going to pass to it which type of feature it's going to be. Okay? All of them have an orientation. Okay? This feature could be vertically oriented, it could be horizontally oriented. The line features could be vertically or horizontally oriented. The checkerboard feature can be diagonally this way. Well, you know what? I wonder. The checkerboard feature, if it's diagonally one way, the mirror image of it, all it does is switch which is black and which is white, right?
Yeah.
So you just use the parity for that. So actually, I think you don't need an orientation for the checkerboard. That there's only one orientation for, because that's what you were asking me. I think you can handle that with a parity, and you don't need a orientation. So that wouldn't be useful if it was a checkerboard. Then you need, where's the upper left and upper left row and column? You need a width for it, and you need a parity for this. Okay, is this weak classifier going to be a -1 or a +1, a greater than or a less than? Okay. And so once you've identified, then you're going to store all of these things into data members. Okay? And then you're also going to have a threshold value, which at this point you don't know what the threshold should be. It's not been optimized yet. Okay? So you're going to set a value, just I set it to be 0 to start with. Okay? Of course that's going to end up being optimized. Okay? Then I have a member function here to get the feature value for some given integral image. Okay, so this is basically give me f j of x, where j is represented by this particular instance of the weak classifier case. Okay, and I'm passing to it an image x, and I want to get the f value back. Okay, so if the kind of feature is an edge, then I need to call the edge feature, pass to it the integral image, pass to it all the other pieces, the things that are stored as data members in this classifier, and then return that value. Okay, so then you're also going to have to add in here if self.kind is equal to line, if self.kind is equal to checkerboard, and make those calls to be able to generate the features for those other features as well. Okay, so that thing returns f. Then we have optimize theta. Okay, we're going to need to determine what is the best threshold for this feature. And interestingly enough, in this paper, they don't ever, this was the hardest thing for me translating the paper into this project, they don't ever explicitly talk about optimizing the features. They sort of refer in an offhand way to it like once or twice. Okay, so I was thinking about it, I was like, okay, well, if we have all of these training images, okay, we need to find what is the best theta value for all of whatever values we have in our training. And how do we figure that out? And in machine learning, that's always one of our biggest things. We've got all this training data. How do we change whatever parameters we're allowed to change to be able to get the best results possible? Okay? And usually, there's lots of parameters to change. I mean, there could be hundreds, literally, of parameters to change, and then it's very difficult to figure out how to choose the best combinations of them. Okay? So at first I was very confused because I'm used to neural networks and this stuff with lots of parameters, but this weak classifier has one thing that we can change. It's theta. We have to figure out what is the best value for theta. There's only one thing to change. Okay? So that makes this problem of optimization much simpler. And so once I realized that, I got to thinking about what these different values of theta are. Okay? And that's where this figure comes in. Whoa, didn't mean to rotate. I wanted to make it bigger. There. Okay. So let's think about a parity plus one weak classifier, where you're asking if the value of the theta is less than the threshold, then it will be a face. Okay? And let's say we choose our threshold value to be negative infinity. Whatever this, the small, the threshold is really, really negatively large. And so if I look at the feature value will essentially never be less than that threshold. And that means that no image, no matter what you pass to it, will ever be considered a face, because the feature value must be less than the threshold in order to be a face. So if you have a threshold that's very small, every image, no matter what it is going to be considered not a face. Okay? So everything that is not a face will be correctly identified with a very small threshold. And everything that is a face will be incorrectly identified. Okay? So I had a training set here that had an equal number of faces and not faces, and I don't think that's true for the training set that you have. But I did one equal just so that we could see that 50% made sense for us. Okay? So I had a set equal here, and all the faces, 100% of the non-faces were correctly identified for a very small threshold. And 0% of the faces were correctly identified for a very small threshold. Okay? If you look at the other extreme end, let's say we have a positive infinity threshold. So every feature value, no matter what the image is, will be less than the threshold, so this classifier will believe that everything is a face and nothing is not a face. So in that case, all the faces will be correctly identified, and none of the non-faces will be correctly identified. Okay? And so then the green there represents the situation where it's the combined classification for this evenly distributed face between face and non-face training set. So in these extreme cases, half of the things are correctly identified, half of them are incorrectly identified, and so there's going to be a 50% classification rate for both the extreme ends of a small threshold and a large threshold. Okay? So as I slowly increase, so let's say I start off with the negative infinity one threshold, and if I make that bigger and bigger, eventually, at some point, I'm going to make it bigger than what some face is going to have a relatively small, and I'm finally going to make that threshold a little bit bigger than whatever that one face is. And so now one of the faces is going to be correctly identified, okay? And perhaps some of the non-faces are going to be incorrectly identified. Okay? And so as I move my threshold from left to right, okay, less of the non-faces are going to be correctly identified, and more of the faces are going to be correctly identified. They're eventually going to cross each other and get to the point where when I get to this side, all the faces are correct and all the non-faces are incorrect. Okay? And so if we look at, so there's no way to know exactly what's going to happen with the combined result. But as it turns out, depending on what the threshold value is, I could get the best possible. This right here represents the best possible threshold. That if I choose a threshold a little bit less than 0, I'll get maybe 58% of them right. Okay, and here's the worst possible threshold. If I choose a threshold of about 25, I'll get fewer correct than if I just guessed. Okay, so that's obviously a bad weak classifier. We would not want to use that one because it's worse than just guessing. Okay, this right here, any of these that are above 50% are valid weak classifiers, but we would like the best possible weak classifier. So we want to choose a value right here that has the highest possible classification rate for my training set. So I want to have, in this case, a threshold of -5 or -10 or something like that. Okay, so in order to optimize my weak classifier, I need to get all of the training data, okay, that includes the image and what its correct label is. Is it a 0 or is it a 1, a non-face or a face? And then we need to vary the threshold. Start the threshold very small and increase the threshold in small amounts. Okay? In this case, these threshold values can only be integers, because remember, they're sums or subtractions of pixel values, and the pixel values can only be integers. So if I start with the smallest value and increment by 1, I'll actually test every possible threshold, because there's no point in having a decimal threshold because I can never have a decimal feature value. Okay? So I start at the lowest, smallest possible feature value, and I increase theta all the way up to the top, and then I find at what value of theta did I get the best classification rate, and that's the theta I want to set. Okay? And so that's what you want to do in this optimize theta. Okay? So what it's supposed to get is a 1D array value of the features for the images. So rather than passing the images themselves, you're going to pass the feature values, which you could get with this function right here. This function gives you the feature values. Okay? So I'm going to pass to it an array with all the feature values for each one of the images, and an array the same size with the correct label for each of those images. Okay, 0s and 1s. Non-faces 0s, 1s for faces. And then I need to run through this. I need to optimize. I need to have a for loop to go from the smallest possible feature value to the largest possible feature value and find which theta gives me the highest thing. And when I find that theta, I want to set self.theta equal to the best value. We originally set it at 0. When I call this function here, I'm going to do self.theta equals whatever the best is. And so this thing doesn't return anything. This doesn't have a return value. The result of it is that it sets the data member theta to be the optimal value. So it returns nothing. None. Okay? So you need to write that function. It's just simply a for loop, really. And then you have to evaluate, I need to get the classification of that feature and then check that classification against what the actual label is. Okay? So, how do I get the classification of a particular value? And that's this function here, predict. So, it's this class is different than the fit predict like you had in the k-means clustering, but it's inspired by it. I use this predict name to say, hey, here is a feature value. Predict for me whether this is a face or not a face. Okay? And this, I actually finished this. This function's done. You don't have to do anything here. All I did was implement that one equation. Okay? It implements this equation right here. Okay, so I take my parity, multiply it by the feature value, check if it's less than the parity times the theta value, and if that's true, return 1, and if that's false, return 0. So that's why it's nice and handy to have this equation there. I've got the equation. It's very easy now to translate it into code. It was so easy, I did it for you. I didn't even feel like it was worth making you write that one yourselves. Okay? So inside optimize theta, I'm going to choose a theta, and then I'm going to predict predict it, okay, and then check and predict that for all of the f's. Because remember, inside optimized theta, f is an array of lots of f's. So I'm going to predict every one of the f's, what it is for a given theta, and check how many of them match what are the actual labels. And go through my for loop of all my different thetas, and then whatever is the best theta, set my self.theta to that, and then end. Okay? All right. So that's how we're going to optimize them. Now you're going to do that once. Let me open up this is the template code for the training the classifier. Okay? So in here, we initialize some things. We glob to get what are the faces and not face file names, and then we loop through all the not faces. We load in the image. We append that image to a list of images. We get what the integral image is. We append the integral image to a list of integral images. Okay. We are going to add. We calculate the features. Oh, that's another function we got to talk about. Get features. Yeah. Okay. We're going to get the features for that particular we're going to get the features for all of the classifiers. Okay, let's see. This guy right here, I haven't talked about this guy yet. Okay, so there's a function called make WeakClassifier Okay, and what this is going to do is going to create a list of all of the 180,000 weak classifiers. Okay, so each element in this list is going to be an instance of the weak classifier class. Okay, with all of the different classifiers. And so in here, let's look at make WeakClassifier. That's just a helper function. It's not a class. Here's this helper function. Okay, and so what we want to do, it doesn't take anything in, and it's going to return this list of weak classifiers. Okay, so it's going to start off as an empty list. Okay, and what I've done here is I've fixed the height to be 6 and the width to be 4 and the row position of the upper left corner to be 6. Okay, so I'm looking at changing the width. Okay, so I have a for loop that loops through all of the possible widths. Okay, I'm sorry, the width is fixed. All the possible upper left column positions. So the width is fixed, the height is fixed, the upper left row is fixed, the upper left column is not fixed. I'm going to loop through that. And you'll notice that I stop once I get to the edge. I don't want to go within width of the left edge of the image, because then my feature will be hanging off the edge. So I don't go all the way up to 19, I go all the way up to less than whatever width the W is. Okay? And so I'm going to loop through do lots different edge classifiers. I'm going to do 2 that are vertical. One of the vertical ones that has a negative parity. One of the vertical ones that has a positive parity. Then the horizontal ones, I'm going to have one with a negative parity, one with a positive parity. Okay, so I'm looking at all the different combinations of parity, of whether it's vertical or whether it's horizontal, and all the combinations of where the column position is for its upper left corner. Okay, now of course that's only a small subset of all of the edge features. We actually need to have nested for loops here to loop through all the possible H's. Nested loop to loop through all the possible W's, and nested loop to loop through all the possible rows. So you're going to have this giant nested loop to look at all the different possibilities of H, W, row, and then whether it's a vertical or horizontal one, and whether it has a positive or negative parity. So here you can see where we're starting to get this 180,000 features. Okay? Then once you get your line features done, then you're going to need to have another set of nested for loops to go through all the possibilities of the line features, where you're going to be creating weak classifiers that are lines instead of edges. And then you're going to have another set of nested for loops to do for the checkerboard ones instead of the lines and edges. But really, it's, once you get it, you're basically going to copy and paste this stuff and just change some of the things around. Okay? And that's how you're going to generate this enormous long list that each element in the list is a different weak classifier. That's all my different J values for the different classifiers is in this enormous list. Okay? It's pretty crazy. So, I'm going to have this enormous list of weak classifiers. And then, in here, I'm calling another helper function called getFeatures. Okay, this is not inside the class, but it's a helper function. And I'm passing to it a list of all of the weak classifiers. And I'm also passing to it a list of all of the integral images. Okay, now these two lists are going to have different sizes. The weak list is going to have the 180,000 or however many it ends up being. Okay, and then II is going to be a list the size of how many images are there in the training set, both faces and non-faces. So they're going to have different sizes. Okay? Then we need to go look at this getFeatures thing. getFeatures. Right here. Okay, we got a list of our weak classifiers. We've got a list of our integral images. Oh, I already read it. Did I already write it? It's done. Hey, wow, look at that. You don't have to write anything for this one. Okay? So, basically what it does is it makes a 1D array of... Okay. Right, okay. So it's going to have a list of all of the feature values. Okay? And so then it's going to loop through each one of the feature values. Okay, so I'm going to go through each one of the feature values. And I'm going... Each one of the... Hold on. We're going to loop through each one of the weak classifiers. So this is one of the weak classifiers. Maybe I should have called this J. That would make more sense if I called this J. It would change with, it would go with the or would it? Let me think about that before I say that. Oh, why won't you let me make this big? Calculate the ith feature. Oh, that's not a list. This is not a list of integral images. That's just a single input image. Okay. Right. Okay, I'm sorry. I didn't read what I wrote there. So yes, this would actually be better as J. So I'm going to take the jth weak classifier. I'm going to take a particular image. One particular image happens to be the integral image of it. Okay, so that's X. Maybe I should have called that. Maybe I should call that X. Okay, so I'm getting my image X. I'm going to calculate the jth feature. So this is F. Feet is the same thing as F. Okay, I'm going to get the jth feature. So I'm going to loop. I got a list of all of my classifiers. I'm giving it a single image, and I calculate the F value for each one of the classifiers for a given image. So I'm looping through all the J's. Okay, in this equation. In this equation, I'm looping through all the J's to find the F value for all of the J's for a given X. Okay? All right. So, I load in a particular not face. I append the image to a list. I append the integral image to a list. And here I'm not passing the integral image list, but rather just that one integral image. So I'm going to get all of the features. Okay? So this is going to be a big long array of all of the feature values for that image. And I'm going to vertically stack it on whatever features are already there. Okay? So it's going to start off with it being empty. The feature starts out empty with no rows There's no rows, but the number of columns equal to how many features there are. Because the amount of elements in the list of weak classifiers is how many features there are. Okay? And so it starts off empty with 0 rows, and then I'm going to vertically stack it. So I've got something that has no rows, and I have something that has 1 row, and I vertically stack that, and then I have feet is now 1 row. And each column represents one of the feature values for that particular integral image. Okay? Then I append a 0 onto the label list because these are not faces, so I'm going to put a 0 onto the list that has what the labels are. Okay? And then we're going to append on a weight, and I haven't talked about that yet. Okay? Then I'm going to go, here I have a feature value with 1 row and a bunch of columns. I loop through, load in the next image, calculate its integral image, call its features, and get all the features for the next image, and vertically stack that on the feet. This is a 2-dimensional NumPy array. Okay? Get the next image, vertically stack it, vertically stack it, vertically stack it, vertically stack it. So I'm going to build a feature 2D array that is the normal orientation of what we're used to. Each row is one of the samples in the training data, in the training set, and each column is one of the feature values. So I have a 2D array that's going to be enormous because there's 6,000 training images, right? So it's going to have 6,000 rows and it's going to have 180,000 columns. Okay? So hopefully you got 16 gigs of RAM on your computer.
My laptop's going to crash. Luckily, I built my desktop. It's going to crash.
Okay. So it's going to be big. All right? And this is nothing compared to doing deep neural network, convolution neural networks. I mean, it's so ugly that you should have a GPU to do them. I mean, I've done them with CPUs. You just have to wait a little longer. But yeah, it gets ugly. Okay? All right. So then it loops through all of the non-images. Then it loops through doing the same thing for all of the things that are faces. Non-faces, then are faces. And the only thing that's different between the two is I append a 1 onto the labels for faces and a 0 onto the labels for a non-face. So we're going to end up with this giant matrix of features. Okay? Because the feature value doesn't depend on the threshold. The feature value is the feature value. Okay? If I have that particular image with that particular feature, there's going to be one feature value and it's never going to change. Okay? So, one of the things I've done here is I've used the pickle command, which I talked about before, right? Okay, and pickle.dump. I think you loaded stuff in the last one, but you didn't write anything. So instead of save, they use pickle.dump. So you dump your pickles. Okay, I'm here dumping the list of integral images to a file name called iilist.pkl. Okay, you probably will want to save the images themselves. You probably want to save the labels. Okay? You probably want to save those feature values because it actually takes quite a long time to calculate 180,000 values for 6,000 images. Okay? And I think when I did this project, I didn't even use all 6,000. Okay? So, you don't have a hidden test set for this problem. Okay, so you don't have to worry about building the absolute best one. You have to make it work with that picture of me. Okay, so it takes time to do these things. So you might want to start off, as in the beginning, you might want to start off just with the first 10 faces and the first 10 non-faces or something. Just so you can do stuff and it doesn't take forever. I don't know. I think I used like 800 of each or something like that. I didn't use all of them. And I was still able to get okay results. But of course, you could build a better one if you did use all of them. See? So it depends on how much your computer cries, how many of those images you might use. Okay, so save all of them. Okay, so then the next time you run your program, you don't need to wait for all that to happen. You can just comment that out and just load them in with pickle instead. Okay, that is a good trick. I only remembered to do that halfway through, but it saves a lot of time. Yeah.
Would it even be worth it to just separate that into two programs, have one
Sure.
that just generates all those files? And
Sure.
one that loads it?
That's fine. That's fine. Okay? So, you're going to save the other important variables so you can use them next time. Okay? Then you also need to optimize all of your weak classifiers. Okay? So for each weak classifier, you need to call optimize classifiers. Optimize theta. Okay? And remember, what you need to do for this is you need to pass to it the feature values for that particular classifier for all the images. So that means for classifier 1, out of this big feature vector, you need to pass to it column 1. The first column are the feature values for all of the different images in your training set. So you're going to pass column 1 to the first, column 0 to the zeroth classifier. Then you need to pass column 1 to the first classifier, column 2 to the second classifier, column 3, etc. So you can see you need a for loop here to loop through all the different classifiers, pass the appropriate column, and all of the labels. Okay? So the size of that column is going to be the same size, at least the length of that column is going to be the same length as label, because those are the correct labels for each one of the images in that column. So you're going to pass the feature values for that particular jth feature, pass the actual labels for each one of those images, and that's what you're going to optimize against. Okay? And that takes time too. You're going to have your 180,000 features, and each one of them you need to loop through from the smallest possible feature value to the largest possible feature value and set what its self.theta is. So that's going to take time too. So once you get that done, pickle your list of weak classifiers, because your weak classifiers will not change after that. For the given training set, you're going to use those weak classifiers, and the strong classifier is going to be built by piecing together many of these weak classifiers. Okay? Now, if you later decide to use more input images, or you later decide, I actually am going to do those checkerboard features after all, okay, you might need to rerun that if you add more features or if you decide to use more images. Okay? But in general, you're going to do that once, and then you're going to run the rest of the code, depending on those feature value, the weak classifiers that are never going to change. Okay, so that gets you to this point here. Okay, and I already did it for you. I went ahead and saved that weak classifier list. Okay, then we're going to have a strong classifier list. Okay. That shouldn't be list. Why is that list? That's just going to be a single one, I think. But anyway, we'll get to that next time. Okay? So there's a class for the strong classifier, and then this loop here is going to loop through the AdaBoost. Okay? So you got some things that you can do for next time. Fill out that weak classifier, finish the stuff for the weak classifier stuff in your features, and see if you can get your pickle files created. Okay? Questions? Ready to go. Let's do it. Okay. We'll see you guys on Monday.